We're now going to talk about the central limit theorem. This is one of the most important theorems in the study of asymptotic statistics. While formally as stated, the central limit theorem just applies to the sample mean, we will see throughout this course that many asymptotic results when we're engaging with estimators hinge upon this central limit theorem. We're first going to discuss what the central limit theorem is, and then we're going to think about sample means or empirical averages of derived variables and how these can also engage the central limit theorem. Now let's just talk a little bit about the statistical or experimental setup that we often think about when we engage with the central limit theorem. Here we imagine we have n independent and identically distributed draws from a distribution f on R. We imagine that these random variables have bounded variance sigma squared, and we let mu denote their mean. In this case, we call z bar n the sample mean, and it's just the average of those n IID observations. I will sometimes also refer to quantities like this as an empirical average, and that is to differentiate it from the population mean, which we can think of as a population average. So we now ask ourselves the question, how does the sample mean behave asymptotically? What happens as the number of samples gets large? Well, we've already seen some results on the behavior of the sample mean as n gets large. We first note that the sample mean converges to the population mean in probability. We can write this as z bar n minus mu as little op1 using Landau notation. Or we could write z bar n right arrow p converges in probability to mu. And in fact, we know a little bit about that rate of convergence, right? We know that z bar n minus mu is big OP 1 over square root of n. So that difference converges to 0 at least at the rate of 1 over square root of n. And we show this result basically using Chebyshev's inequality and the fact that the variance of the sample mean scales like 1 over the number of observations. So we can think of this as describing maybe the 0th order behavior of the sample mean, or what I will refer to as the 0th order behavior, that the sample mean converges to a point, mu, the population mean. But it's often of interest to think about what the shape of the sampling distribution for the sample mean looks like as the number of observations gets large, and we sufficiently zoom in on mu so that it doesn't just look like the sampling distribution is converging to mu. Right? Again, we either zoom in on mu or we expand that sampling distribution out so that we can better understand aspects of the shape beyond just its width. And we might think of this, the shape of the sampling distribution, as the first order behavior of z bar n. So let's look at an illustrative example. Let's return to the exponential example we've seen before. Let's imagine that our random variables are drawn IID from an exponential with rate 1, and let's look at the sampling distribution of the sample mean. So again, we can look at the sampling distribution for a single exponential. Just a reminder, there should be no mass to the left of 0, but that's just a little bit of computational error in this case, or smoothing error. We can look at 2 exponentials, 3, up to 5, up to 60, up to 150, up to 500, and all the way up to 5,000. And as expected, we see that the mass is concentrating around the population mean, which in this case is 1. So this is really describing just the 0th order behavior here. Now, again, I'm interested maybe in that first order behavior. I don't just want to know that the center of the sampling distribution stays at 1, that the width is shrinking. I'd like to look at other aspects of the shape beyond just that width. So to do this, let's zoom in on that sampling distribution around its center 1 so that we can see what it actually looks like as opposed to just, well, it's shrinking. One question we might ask is how strongly should we zoom in? And we saw previously in our discussion of probabilistic Landau notation that in fact square root n is really the correct amount of magnification here. And this result that z bar n minus 1 is big OP 1 over square root n really strongly hints at this. It says we need to zoom in by at least magnification of square root n, that if we zoom in any less, the sampling distribution will still appear to concentrate. And again, it turns out that square root n is the correct amount of magnification. And to do this, I'm going to change my x-axis range rather than going from negative 3 to 3, I'm now going to go from negative 3 over square root n to 3 over square root n. So now we've centered our sampling distribution. We've subtracted 1 so that our sampling distribution is centered at 0. And as we increase n, we see that our sampling distribution does not appear to concentrate around 0, and in fact seems to stabilize to this bell-shaped unimodal density. Right? So this was the correct amount to zoom in. And in fact, empirically, it appears that this density converges to maybe a stable density or a density that we understand. So it turns out that zooming in is not ideal when we are trying to engage with this definition of convergence and distribution. So instead of zooming in, changing the x-axis labels, we're going to think about stretching our sampling distribution so that the x-axis can remain on the same scale that it always was, regardless of how large n is. So stretching a sampling distribution that's centered at 0 is actually equivalent to considering a sampling distribution of a scaled version of our original random variable. So what does this mean? It means rather than that whole zooming in exercise, we might instead look at this sampling distribution of square root n times the quantity z bar n minus 1. Right? Now, rather than zooming in, we're really just stretching that sampling distribution such that it's always on that original scale. So let's look at what happens here. Again, for n equals 1, this doesn't change anything. However, as n increases, the plot looks exactly the same, only the x-axis label now is different. Rather than the x-axis label getting closer and closer to 0, it remains constant, and we have just stretched the sampling distribution such that it remains on the same scale. So again, these should look very, very similar to the densities that we looked at before. It's just that the x-axis is now remaining the same rather than changing. Something interesting to note here, I have overlaid as a dotted red line a Gaussian distribution with the same variance as my scaled sample mean distribution. Right? And we see that the two match almost perfectly, and in fact, in this case, both of them have variance equal to 1. Another way of thinking about this whole scaling exercise we engaged with, going back and now back forward, we are scaling these random variables such that the variance is always the same no matter how large n is. All right, so now I think we're ready to formally engage with the central limit theorem. So let's just remind ourselves again of our setup. We have n random variables that are drawn independently and identically from a distribution on the real numbers. We imagine that they have a variance that exists that is less than infinity, and we let mu denote the mean of these random variables. Then the central limit theorem tells us that the sample mean, suitably centered and scaled, so if we take the sample mean, subtract off the population mean, and scale it by square root n, stretch it by square root n, then we have that it converges in distribution to a Gaussian distribution with mean 0, and with variance sigma squared, which is the same variance as a single observation from our original distribution, and that same constant variance that this scaled sample mean has for actually every value of n. So again, this is incredibly important and kind of profound. It says regardless of the original distribution that our random variables are drawn from, so long as the tails are not too wild, the sampling distribution of the sample mean will converge to a normal distribution, right? It's saying that this normal distribution is a very important and central object and canonical. And I might colloquially call this the first order behavior of the sample mean, while the 0th order behavior said the sample mean under very mild conditions will converge to the population mean, and that sampling distribution will fully concentrate there. The first order behavior would say, and if you scale up by square root n, which is roughly 1 over the width of that sampling distribution, the shape of this distribution will look like a Gaussian. So the central limit theorem, as we just looked at it, seems to only apply to sample means and population means. And as stated, that's entirely true. However, there are a lot of things that are what I'll call empirical averages, which I often use to mean a sample mean of some transformed random variable. So let's consider estimating the variance, sigma squared. And in this case, let's use an estimator that we often don't use in practice and may not have access to, and we'll see why in a second, but I'm going to call it sigma hat squared. And it's going to be an empirical average of this quantity zi minus mu squared. So in order to calculate this estimator, you would need to know the population mean. So again, often we can't do that. But for now, we're going to think about this estimator because it's maybe going to help us relate to the central limit theorem. So this estimator, sigma hat squared, is just a sample mean or an empirical average of these transformed or derived variables. So if we let yi be defined as zi minus mu squared, then sigma hat squared is just this sample mean or empirical average of these yi, and each of the yi are independent and identically distributed. So based on all of the theory we've already done, we could say, okay, sigma hat n squared minus sigma squared converges to 0, and it converges to 0 at least at a rate of 1 over square root of n. And then more specifically, we could apply the central limit theorem, and we could say square root n times the quantity sigma hat squared minus sigma squared converges to a normal distribution with mean 0 and with some variance that's a function, in this case, of the fourth moment of z. Again, what we've noted is this variance estimator is an empirical average, and so the central limit theorem will apply to this estimator just as well as it applied to that simple sample mean. So here's what I'm going to call an almost example, and this will be really important as we move forward, but we can't quite apply the central limit theorem here. And we're going to run into a lot of these so-called almost examples that we're then going to have to do some work to relate them so that we can use the central limit theorem. And in fact, there's going to be something called asymptotic linearity that will give us a framework for doing that quite generally. So let's consider what we might do when we're actually estimating the variance. And when I say actually, I mean generally we don't know the population mean. So we take that sigma hat squared estimator and we swap mu, the population mean, for z bar n, our sample mean. So here we have an estimator for the variance, sigma tilde squared, that is an empirical average, but now each of these yi that we're averaging is zi minus z bar n, the quantity squared. So again, it is a sample mean of these yi, however, the yi are no longer independent. All of these yi have that z bar n quantity that is random in them. So that couples all of our yi. So we can no longer directly say, great, the central limit theorem gives us this result we had before. It turns out we can still relate this to the central limit theorem, but it's going to take more work, and we're going to do that moving forward. And in fact, once we do relate it to the central limit theorem, we'll see that this estimator actually has the same first order asymptotic behavior as that previous estimator sigma hat squared. However, again, we can't directly apply the central limit theorem. We have to do a little additional work to get this result.